To begin, check the levels of all the fluids in the machine. Empty the waste if necessary and fill all the reservoirs including the sheath, water, cleanser and steriliser, as well as the speed beads. We have indicated some suggested minimum and maximum amounts with black lines on this machine. Unscrew the lids and top up and place the bottle, pushing all the way back to where there is a level sensor. Turn on the machine by pressing the button on the front. The two PCs controlling the machine should also be turned on. Launch the Inspire software and click the Startup button, which will start the machine and run the assist tests according to the manufacturer's instructions. This takes approximately 45 minutes. Once all the assist tests have passed, you will see a green circle at the bottom right of the software. If it's orange or red, you will need to check the machine and rerun any failed tests. You are now ready to run your samples. To set up an experiment, close the assist test window, and we first need to select the detection channels needed for the experiment. Refer to the instrument manual to determine which channels are required for the fluorophores in your experiment. Click any channel button at the top and tick the boxes of the channels that are required. Remember to keep the bright field channel set here as channel 1 and 9 and the side scatter channel set here as channel 6. On the right-hand side in the Illumination tab, turn on the lasers required for your experiment by toggling the buttons. Set the laser power in milliwatts to the maximum to start with. To see the maximum and minimum settings, hover your mouse above the numbers. We may reduce the laser power later depending on the sample, but it is best to start at the maximum and go from there. The bright field channel are set to channels 1 and 9 by default, and there's rarely a need to change these. All other settings we can consider once we have a sample running. There is a choice to place the side scatter in channel 6, which will prevent the use of fluorophores such as PE-Cy7, or channel 12, which will prevent the use of fluorophores such as APC-Cy7 or near-infrared dyes. You must choose one. In the software, we can create some of the plots we need. Start by pressing New Scatter Plot and select the X-axis feature Area M01 and the Y-axis feature Aspect Ratio. The resulting plot uses the data from the bright field image to calculate the area and aspect ratio of any event, and it enables us to choose the cells of interest for our study. You can then press the new histogram and select Gradient RMS for channel 1 as the X-axis feature. This plot assesses the quality of bright field image and allows us to select the in-focus events. You can then set up any plots relating to your samples. In this first example, we're going to look at cells stained with PHITC, which is in channel 2, and propydium iodide, which is in channel 4. So I'll go ahead and create histograms for those two channels. And then I will create a scatter plot where the X-axis feature is raw max pixel for channel 2 and the Y-axis feature is raw max pixel for channel 4. The raw max pixel values will help us check for saturation. To begin, press Load. Thoroughly vortex your sample. Your sample should be as concentrated as possible and ideally be 30 to 50 microliters and have absolutely no bubbles. Insert your tube with the lid facing towards you. On the dialog box that appears on screen, press OK. There's no need to change the value in the box. The machine will estimate the volume of the sample, which will be displayed at the top right of the software. You will begin to see cells appear on the screen. We can now continue with the setup of the machine with the sample running. The first thing to decide is the level of magnification required. In general, we want the image of the cell to fill the frame. If the cells are large and do not consistently fit within the frame, then reduce the magnification. The pixel size is 0.3 microns with the 60 times objective, 0.5 microns with the 40 times, and 1 micron with the 20 times objective. You should note that the 60 times objective is the slowest, and samples take 3 times longer than the 40 or 20 times objectives. It is possible to increase the speed, but this causes the loss of resolution as the machine starts to bin pixels together. Therefore, in most instances, we run the machine on the slowest setting for the objective. For this sample, the 60 times objective seems acceptable. Next, we will select our cells of interest, and to do this, I will create a rectangle region and draw around the single cells. Single cells have the highest aspect ratio and an area greater than the smear of debris and speed beads which are apparent on the left of the plot. The other population, with low aspect ratio and high area, are aggregates of cells. We can view the events in our single cell region by selecting it on the population drop-down box. If you want to check what you are gating is correct, move the region and view the cells that are gated. Here you can see the cell aggregates and coincident events. We can also see the debris and small speed beads which run through the machine at all times. Once you are happy with this selection, we can move on to the focus of the cells. First, apply the single cell region to the histogram displaying gradient RMS. Right-click on the plot and select Graph Properties, and at the top select Single Cells and press OK. The gradient RMS, or root mean square, assesses the variation in pixel intensities from the bright field image. In-focus bright field images have a lot of detail and have a high gradient RMS score, usually 50 and above on this particular machine. Out-of-focus events have little detail and often appear uniformly bright or uniformly dark. So we can create a region around the events that are in focus. We can select to view those at the top drop-down menu. So our two quality control regions are in place to identify our single in-focus cells, and we can apply these to our remaining plots by right-clicking each plot in turn and choosing Properties and selecting the single in-focus cells at the top. You may notice that we're not seeing any green looking cells. The appearance of the images isn't actually important in capturing the data and can and should be adjusted in analysis later. However, so we can see what the cells look like as they pass through the machine, we can adjust the display settings by using the button at the top left of the screen. Once open, we can click on Channel 2 for FTSE and adjust the maximum and minimum intensities. Move the left-hand vertical line to the left-hand side of the histogram and move the right-hand vertical line to match the highest pixel intensity in the image. Press OK and you will see that we can now see the green of the FTSE. These cells don't have any propylium iodide, so you can't set up those display settings yet. Our next job is to look for saturation and adjust our laser power accordingly. Saturated pixels are seen in the images as red pixels. There don't appear to be any saturated pixels on this sample. However, we can use the raw max pixel scatter plot that we created at the start to quantify this. The raw max pixel plot shows the raw pixel values for our images. The maximum value of the camera is 4095. So if we see a significant proportion of pixels at this very highest level, then we know there is too much saturation and we will need to reduce the laser power. I will press load again, and while the machine is flushing the sample line, I'll prepare the next tube by vortexing it. This is a sample of the same cells, but this time labelled with prapidium iodide, which is an orange fluorophore, and I'm anticipating that the cells will have stained very brightly. So we can see the machine has estimated the volume and is injecting the sample. We can see immediately the cells are very bright, and they are so bright that it is actually affecting the gradient RMS of the bright field. So I know that we're going to need to reduce the laser power, and this dye is best excited by the green laser, so I will begin to reduce this one. Reduce it in steps until you reach the minimum power. In this case, they're so bright that we'll also need to reduce the blue laser, as PI is excited by both lasers. As I reduce the blue laser to 20 milliwatts, the data becomes on scale. The cells appear where we expect them in the area and gradient RMS plots. If we look at the intensity values of channel 4 for prapidium iodide, they are of good brightness values, just below 10 to the 6. Now we can set up the image properties for prapidium iodide. Click on the display settings and click on channel 4. Adjust the right-hand line to the maximum of the graph and the left-hand line to the minimum of the data. Looking at the raw max pixel plot, we can check for saturation, which if I set the scale from 1 to 4095, we can see there are no events at the 4095 value, which indicates we no longer have saturation. Okay, so we've set the laser power for both dyes. We have chosen the magnification. The only remaining option is to change the speed in the fluidics, here on the right-hand side. Usually it's best to leave the machine on its lowest speed. As I mentioned, the 60 times objective makes the machine runs 3 times slower than the 40 or 20. But if we increase the speed on the 60 times objective, the machine will bin pixels together, reducing the resolution from 300 microns to 600 microns. So it would be more efficient to run the 40 times objective on the lowest speed, giving 500 micron pixels, but overall a much quicker speed. All our settings are now complete. We can acquire our data. Start in File Acquisition, select where the data is to be saved. Change the name. Choose how many cells to count. Here, let's say 5,000 cells, and we can use our focused single cell gate. You have the option to collect just those, or if we unlink this, you have the option to save all of the data, which is a safe way to do it, and we can adjust the cell gate later in the data analysis. Press Acquire and the machine will run and save your data. When finished, return the sample and run any other samples that you have. Save a template by pressing File, Save Template. Next time that you run your samples, you will not have to set magnification and laser powers again unless your staining has changed. So in this example, I'm looking at some PBMCs stained with 2 antibodies, CD4 labelled with brilliant violet 421 and CD8 labelled with PE eFluor 610. And I have a single colour control for each stained with just a single antibody that I can use to generate the compensation matrix. I already have a template where I've previously selected my laser powers, speed and magnification. So I'll start by clicking File, Load Template. Go to Compensation and press Create Matrix. It asks you to load the single colour controls. So press Load, put the sample in and press OK. Verify the system finds the correct channel. And it's got it right, this sample is brilliant violet 421, which is in channel 7. So we can press Next. Set the acquisition file name, destination and population to save and press Acquire. Return the sample and load the next control sample to repeat the process. In this case, it has got the wrong channel, so I'm going to correct it and tell it that our PE eFluor 610 will be best in channel 4. Press Next and Acquire. Return that sample and you can see now that it has calculated the compensation coefficients for channel 4 into all the other channels and channel 7 into all the other channels. Press Finish and save the compensation matrix. With all settings remaining the same, you can begin acquiring your experimental samples. Load the sample, name the sample and choose the number of cells to acquire and which population to save, and press Acquire. The saved files will need to be analysed later in IDEA's software. Remember to take your compensation files, which are the ones with no BF in their title, the compensation matrix CTM file, as well as the experimental samples which end in RIF, the raw image files. Check all the solutions are filled up within the machine and press the shutdown button on the software. The machine will clean, sterilise and turn itself off.